Hey gang, and welcome back for another exam solutions walkthrough for the exam Organic Chemistry 2, Exam 1. Alright gang, if you are here, that probably means you're most likely preparing for a test. So before we even get involved with the practice exam, good luck, take a deep breath, you're gonna crush it, you're gonna be fine. However, since you're here, that probably means you attempted the practice exam here on jOeCHEM, and you're looking for explanations to the answers you saw on the solutions key. Well, my friends, you're in the right place. In this video, we're going to walk through that exam and hopefully give you the explanations that you are looking for. So let's get started. Rolling into problem 1 on this practice exam, we kind of have 4 complete the reagent or little mini synthesis type of problems. So if we take a look at the first one, right? Now these I've mentioned in the past, I don't think there's any problem if you start from the beginning and go forward, versus doing retro-synthetic analysis. Whatever you're, feeling more comfortable with, I'll do a little bit of both. So what I like to take from retro-synthetically, like the information from my product, is the relationship between the groups on the ring. So you can see here that we start off with this we have phenol, and we see that we still have the OH right here, and we have an ortho relationship in our product, a 1-2. And we know when we add groups to a ring, sterically, we like to put them para first. So it is interesting, and the information we can gather here is that we did not brominate in the para position, and we then brominated in the ortho position. So you might be thinking, blocking group. So what I would first do on this, this problem is I would absolutely put a sulfonyl group on my ring, and you'd see if I work over here, I'm going to use a circle. That would put an SO3H right there. Then, with that group blocked, right, the alcohol is still the predominant directing group, directing ortho-para. It can no longer direct para because that's where we put this big, bulky sulfonyl group that's only blocking. Then you can bring in the cavalry in terms of brominating, which will then put the bromine there because the OH, the ortho-para director, the stronger directing group, will have no choice. It can't put it para. The bromine, it will have to place it in the ortho position. And then we don't see any trace of our sulfonyl group. So remember, to get rid of that, our sulfonyl groups, you need acid and heat as well. It just erases the sulfonyl group, and that does it for the first part of problem 1. So moving on to the second problem. So again, what kind of relationship do we see in our product? We see a meta relationship, okay? And we see, interestingly enough, even though both of these groups are meta, neither of them look like meta directors, okay? So what happened here? So this is a case where maybe it helps to think about, okay, maybe the final step was a reduction of some sort, and both of these groups looked like this before said reduction. And that gives us a little bit more to work with. This makes a little bit more sense. Now, you might think to yourself, okay, I can just nitrate and then Friedel-Crafts acetylate and then be good to go. I would caution this though, when you're doing these problems, just think about which group is best to put on first. In this nitro group, should you expand it, you'd see that there's a positive straight up charge on that nitrogen. In this 3-carbon carbonyl group, you can see that there, in that the ketone, the carbon directly off our benzene ring is only partially positively charged. So remember, we want to make sure we order and add these groups on in such a way that they deactivate, if they will deactivate our benzene ring, they deactivate it as less as the least amount possible when we're putting on successive groups. So what I would do first is I would do my Friedel-Crafts acylation first. So I'll bring in my AlCl3, I'll bring in this 3-carbon acid chloride. So that first step would give me something like this. Okay? Then I will nitrate, because I still need this is a meta director, I still need that. I can't convert it to an ortho-para director yet. And I know this is not the most amazing reaction, but given what we're posed with creating, this is what we need to do. Once I do that, I get my nitro group meta, because you can see 1, 2, 3. Those two groups have a meta relationship. And it's then that I have a couple of different options here. You can use the H2PDC. You could also use the Clemmensen reduction, and I included that on the answer key because I feel like people really highlight that the Clemmensen reduction attacks or singles out carbonyls in the benzylic position, but it also converts nitro groups to amines, just like H2PDC. So H2PDC absolutely works here. I'm showing you the Clemmensen reduction, but this is the order. I would absolutely do it in this direction first because the nitro group is going to deactivate the benzene ring so much more than the Friedel-Crafts product, or the ketone right there. Clean up some room here. Okay, moving on to 3. Okay, so again, you can see an NH2 and then a sulfonyl group, and they have a para relationship. And maybe you're thinking from our helper reaction video, you know that amines are super basic. Absolutely. So we do need to be careful when we are doing this reaction. Be mindful of the fact that we could have to protect this amine to prevent it from becoming a meta-director. So I would say the first thing we need to do is actually put some source of nitrogen on this ring, and I would agree with that. I'm going to use a lot more room over here. I'm going to put a nitro group on first. Then we need to reduce it to an amine. So again, you have your choice of, and I'm just going to make sure I stay consistent with my answer key. I'm going to, here I used H2PDC, but you absolutely could use the Clemmensen reduction if you wanted to. Okay? That turns this, after step 2, that turns this into an NH2. And then we need to protect our amine. Remember, you can throw in your acetyl chloride, and what that does is it takes our amine and it makes it an amide, which I know we don't have a whole lot of experience yet, but that is going to come. Basically, all this does, remember, it takes our amine and it makes it less basic, so we can then subject it to acidic environments and not worry about things going haywire. So at this point, you bring in the H2SO4 and the sulfur trioxide. That then puts your sulfonyl group on, and this is still an ortho para director. Absolutely has electrons. It is electronegative directly off of your benzene ring, and I'm going to put 5 over here. We don't see any trace of the acetyl group there, so you just need acid to unravel that. The acid alone just takes away the protecting group. You need the heat for the sulfonyl group. Okay, and last but not least, you can see down here, we have a sulfonyl group and this chlorine up here. How do we get a para relationship between them? Well, remember, this is a meta-director, and it's also super deactivating to the ring. We'd almost be better off with a regular benzene ring, and that's what we need to do. The first step here is actually just removing your sulfonyl group, just getting rid of it, just bringing it back to plain old benzene. So after the first step, we just get a benzene ring. And then you bring in the chlorination reagents, the Cl2, the AlCl3. That's going to put a chlorine right here. And remember, while these are slightly deactivating because of induction, they are still ortho-para directors. The resonance proves that. So to get that sulfonyl group in that para position, we just need to bring back the sulfonyl reagents to bring back the sulfonyl group, and we get it right here. So it is silly that we kind of have to remove what we start with, but to get that relationship, that's what we have to do. Okay, gang, that was problem 1. On to 2. Okay, gang, in problem 2, we have a Diels-Alder reaction handed to us, and we are told that given, what we're shown, product A is observed and product B is not observed. So I'll put an X here, I'll put a check mark here, and we need to explain why that is the case. So just doing a little housekeeping first. Oh, and I need to do a little bit of housekeeping of my own. Forgot this right here. We can see that 1, 2, 3, and 4, 5, and 6, and you can see in both rings right here, 1, 2, ethyl group on 3, nothing on 4, deuterium on 5. We have the ester on 6, and same deal over here. The only difference between the two products that are handed to us is the stereochemistry at 5 and 6 relative to 1. Here you can see the ester has the same stereochemistry as the O-methyl, and here you can see the stereochemistry is different. So if we were to kind of dot our little pocket of formation, maybe one thing that tips you off is this is an out group, this is an out group, and they have the same stereochemistry here, but they do not have the same stereochemistry there. So what's going on? So what this problem is absolutely getting at is which product, or justify where the endo effect is shown. So what we will see is that this is the endo product, this is the exo product. That's why we don't really observe B, but we absolutely observe A. Okay, so if you didn't pick up on that, what would help you out? Let's just assume that we didn't even know A was the endo product. Let's draw a transition state, because you can see that clearly this is what is forming. We know the transition state and the endo effect are, that's where we see the endo effect manifested. So what we can do is we could show, and I'm just going to draw the diene hovering over the dienophile. Okay, so this could be carbon number 1, 2, 3, 4, and then we'll do 5 and 6. Okay, so remember, on carbon 1, we have this O-methyl, and remember, I have a hydrogen over here, and it's this hydrogen that really is very boldly sticking out in space over here, as opposed to being back over here. The O-methyl group, on the other hand, that's where it is living. It is living back over here. Okay? Nothing on 2. And then remember on 3, we have what ends up being a planar ethyl group, right, off of an sp2 carbon. So just stick it on there. Now for 5 and 6, that is the key. So remember, so in A, we can see that these two have the same stereochemistry. And I'm looking at ester first, and remember what the endo effect is at all. The endo effect states that if you have groups, right, which electron withdrawing groups do, they have, this carbon's sp2. This oxygen is sp2. We can either put that ester over here or underneath the approaching diene, or from, the same side of where the diene is approaching from. And that's what we want to do. Even though sterically that doesn't, seem intuitive to us, we absolutely want the ester to be over here, because the p orbitals in this group, right, that's sp2 and that's sp2, these p orbitals interact with these p orbitals to stabilize the transition state, and that's what the endo effect states. And that is why we observe A, and that's why the ester and the O-methyl have the same stereochemistry, because they're facing the same direction, okay? And to just round it off, you see that the ester and the deuterium are on different sides of the double bond right here, so the deuterium must be over here as opposed to being this way as well. So this is the transition state we see. We do not, this is not on the answer key, we do not observe this. We do not observe that. This is the exo product, because you can see that the the ester and the O-methyl have different stereochemistry here, and the deuterium and the O-methyl have the same. But this lacks that wonderful stabilization from the p orbitals in the electron withdrawing group and our diene that we do see that we, reality reflects here, okay? So just showing you this, this diagram explains everything. You can just say the endo effect is reflected here. It is not for product B, it is for product A, and that is why we observe A and not B. Okay, gang, that was 2. On to 3. Okay, gang, in problem 3, we have to explain why this sulfonyl group is a meta-director. And I know we've done similar problems on the worksheets if you've done those, but you would be so surprised as to how many people I've seen miss this type of, in my opinion, gimme question on exams, even when it's just resonance. But, so we have our group right here. So the first thing we need to do is actually redraw this and expand the sulfonyl group, right? Because we will have to draw resonance inside of it. So sulfur can expand its octet and has 6 bonds. 1, 2, 3, 4, 5, 6. And you can see it's very partially positive because it is bonded to 3 oxygens. Some double bonded. So here, we know this is an electron withdrawing group, right? A very good one at that. So this is going to be sucking electron density out of the ring via resonance. A resonance move we can draw to reflect that is double bond goes out, and then we boot one onto oxygen right there. Now at this point, after you've done that, you can absolutely just collapse this back into its abbreviation, because the charges will balance out. Actually, just kidding. But you can feel free to do that, or we can just leave it expanded. O minus, double bond right there. Okay, and then we didn't touch this, but we have a positive charge right there. And then at this point, it's just ring around the rosy, right? We can swing this over right there, draw another result of our nope. Sorry, just a force of habit, just going on autopilot. Sulfur, O minus, this, and then that. And then positive charge down here. And then last but not least, I'll draw a small arrow. We can go ring around the rosy one more time. Then we have this, sulfur, OH, double bond, O minus. Okay, so as you can see, if I were to redraw the sum of this, right, and this is, that as well, we get a benzene ring with our sulfonyl group, but because of the resonance, we see we have a partial positive on orthos, as well as para, and for EAS, where we're putting on additional positively charged things, right, we will want to direct to whatever is the most negative, and here what that means is the least positive. So this explains how the sulfonyl group directs. Okay, gang, that does it for 3. On to 4. Okay, gang, rolling on into problem 4, we have this reaction right here where we need to mechanistically explain the array of products that we get here. So what you can see is we have almost a conjugated system, and we're going to subject this organic structure to NBS. And remember, NBS is how we're going to, that's how we do bromination, radical bromination. We can't use the Br2, H nu, and light when we have double bonds present, because remember, if we introduce a large quantity of bromine, these double bonds will just undergo an addition of bromine across that double bond. So NBS is our way to safely, brominate radically. So hopefully what you can see is we have sp2, 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 sp2. So even though this is an allylic position down here, and I'm not saying a product doesn't form here, but the problem is stating we get this array of products, and hopefully it makes sense that this position is very favorable to make a radical on, because it completes a 1, 2, 3, 4, 5 carbon. It would create 5 carbons in a row to be a conjugated system. So you don't have to show this part so much, and I did in the answer key, but when you have this bromine radical, you will have a CH bond, you'll have a hydrogen get plucked, you will then create this bromine radical right there. Now at this point, right, we know that another bromine, right, you could run into another Br2 or what have you, and that's a single-headed arrow, right? Single-headed arrows are out. That's how you would get this product up there, right? Just right on the original carbon we create the radical on. But remember, this is reactions of conjugated systems. So I'm going to draw some resonance here. I'm going to do this in, I'll do this in red. We could do 2 different, actually, what I'm going to do is I'm going to redraw I'm going to redraw that radical structure right here, and I'm going to redraw it right here to explain the resonance and the reactions we get. So this is just resonance where I took this structure and redrew it down here. To explain the top right structure, I could swing that down, swing this down, and put a radical on the terminal carbon so that we would get this right here. Then you would brominate, so we grab bromine, do bromine, and then we get the structure over here. And then, last but not least, we just have to draw resonance the other way. I could swing the radical electron down there, I could borrow 1 electron from over here, and then boot the last one on this carbon right there. And that would give us radical electron here. And we get this structure, which you see is a precursor. Once we add bromine, whoa, some ugly arrows going on. And then we get, crossing arrows, this over there. So really, gang, this was just about realizing where the radical needed to go right off the bat, not getting confused, which hopefully this at least showed you where, you know, the radical probably went at first, and then just drawing the resonance and showing how you get the second and third products. Okay, gang, we're humming right along. Stick with me. Going into problem number 5. As we start problem 5, we can see we have, problem 5 has 8 total complete the reaction questions, so here are the first 4. So if we take a look right here, looking up top. So you can see these are the reagents for nitration, and we're going to do this on a benzene ring where we technically have 2 groups. So off of this ring, right, you see we have a partially positive carbon, so right, partial positive, it's a meta-director, it's going to deactivate, and then we have a slight activator in just this alkyl group. So this alkyl group will be calling the shots, right? And we know it's an ortho pair director. So when thinking about where this nitrogen group is going to go, it will absolutely direct para. So 1, 2, 3, and 4, which does coincidentally line up with the 1, 2, 3 meta director. So it does work out in both cases. So our product looks like this. Okay, that's the nitration. Then down here we see we have bromobenzene and the reagents for a Friedel-Crafts alkylation. Now remember, when we alkylate, our carbocation shift hats need to be on. So we can see that classic, isobutyl chloride. We see we're going to make this carbocation at first, and then we'll rearrange. So really, we stick on a T-butyl group. And remember, bromine, ortho pair director, even though it is slightly deactivating, still an ortho pair director. So we're absolutely going to be putting the T-butyl group on right there. Okay? Now, this problem, which is probably the one that's maybe the trickiest. So let's even come back to this last. Let's look down here. So you can see we have this, this methyl and sulfonyl group paired to one another, and all we're subjecting this compound to is acid and heat. So this is just going to be wiping away this sulfonyl group. So all we're going to have left over here is methylbenzene, aka toluene. Okay? Alright, so for this last product, this is going to be, so hopefully what you can see is, this is a diene, this is a dienophile. The twist here is they gave this to us in an S-trans format, so we need to convert it to S-cis first. That's the first thing we need to do. So, just make sure, just draw your S-cis template first, and then what you can even do is number 1, 2, 3, and 4. So just take it one double bond at a time. So you can see when you have this NH2, wherever the NH2 is, do you see how when you quote-unquote walk the double bond, we cross the double bond? So we need to make sure that, so from here or here, do you see how with this position, we actually do cross the double bond? From here, we do not cross the double bond, so the NH2 has to go up top. I'm going to clean this up a little bit. Okay? The T-butyl group on 3, you just have to stick that on. No worries where it goes. And then the deuterium. So do you see how the deuterium, on the other hand, does not cross this double bond when you walk it? So the deuterium actually has to go here, because when you walk this double bond, you don't cross it. Okay? So that's how you can convert S-cis to S-trans pretty easily, in my opinion. So to keep this numbered 1, 2, 3, and 4. Okay? Now the last thing we need to do is actually place this group, make sure charge-wise and stereochemistry-wise, we're good to go. So what I'm going to go ahead and do, so hopefully what you can see is, with this and this is our partial positive end down here. And then with this electron donating group up top, I hope what you'd see is if we do this, then we do this, and then we do this, we have the delta minus on the bottom. So if we lined these up just like so, electronically, we are good to go, okay? But stereochemically, we have some problems. So let me clean this up. We actually need, so we need to make sure we reflect the endo effect, right? And that means, given our in-out conventions, that these electron-electron groups have to be out groups. So I'm actually going to flip this horizontally to make it go like this, because we know that when we have our electron withdrawing groups, as we draw them on flat paper to be out, then that reflects the endo effect in our transition state. So this is how we want to line these groups up. 1, 2, 3, 4, 5, and 6. So if we draw this product over here, remember, start with your template ring. This is 1, 2, 3, 4, 5, and 6. And we know, just to even get a little gimme, there's no stereochemistry on 3, so that's just going to be that T-butyl group. Okay? So remember, out groups have the same stereochemistry, so I'll just pick the out groups to be wedges. So I'm going to wedge my NH2. I'm going to wedge my ketone. And then the deuterium and this methyl group are both in groups. They have to have the same stereochemistry, opposite the out groups. So that's going to be a dash for the deuterium and a dash for this methyl. And because of every stereocenter that we created, being a result of the Diels-Alder reaction, I can then write plus an enantiomer. Okay? So that does it for the first 4, gang. Let's finish out 5 with the second 4. Okay, gang, to round out problem 5, talking is hard, we have 4 more complete the reaction questions, so let's just get after them. So, in this first problem, right, we start off with bromobenzene, but then you see a familiar face. We see magnesium, right? So what we're going to do in this first step is create a Grignard reagent. So I'm going to go ahead and just do a little bit of work where I have some space. You can see I have MgBr. And then we're going to attack 2 carbons right there, okay? So what I hope you're going to see is after that attack, right? Maybe I'll do some work over here. We're going to have this. 1, 2 with an OH right there, right? So that's where the OH goes. We just attach the 2 carbons onto the benzyl carbon right there, the aryl carbon, I should say. So then, and then 2 and 3, right? Because we have to quench the negative charge. At first, we'll have just an O- after the Grignard attack. The H3O plus cleans that up. And then we see MnO2, manganese oxide, and that's one of our oxidation paths for benzylic alcohols. So this works on benzylic alcohols to oxidize them from, whether they be just a primary OH, benzylic, like a primary benzylic OH or a secondary benzylic OH. So what this does and gives you after the fact is you do a Grignard reaction, but then you get a carbonyl back on that benzylic carbon. So you can see the evidence of the 2 carbons from the Grignard reaction, and we have oxidized it back up to a carbonyl. Okay? Now, for this problem right here, we are just doing bromination, but on which benzene ring? So remember, if we look at each one individually, so this benzene ring, really, if you want to think about it, it has this carbon piece right here, okay? And then this one over here, look at that, it has a halogen, okay? So this ring, slightly deactivated. This ring, because of the fluorine, right? Because of induction, this benzene ring, relatively normal, but if you want to think about this right here, lends a little bit of electron density. This is the ring we're going to work with. The fluorine pretty much takes the other ring out of contention in terms of interacting with it, and we will work with the other benzene ring that is not hindered by, a pre-existing halogen's deactivation, albeit slight, right? So, at this point, this group just becomes one big giant group right here, so we will absolutely direct para, right? This is an ortho, since this is this alkyl, right? Ortho-para director. We're absolutely direct para, and that's where the bromine will go, okay? So, down here, we can see Br2 light and heat. And you might be thinking, why aren't we using NBS? And yes, while we had to use NBS for conjugated systems, remember, for aromatic systems, they're so stable that they're not going to disrupt themselves. Remember, that's why we have to use the special catalysts we've been using. So this is completely fine. However, the most stable radical we have out here, it's not going to be the tertiary carbon. Remember, resonance trumps all. We're absolutely going to create a benzylic radical, right? This question seems kind of silly and redundant, but it's just to show you that even though this is quote-unquote secondary, it's benzylic, and that's much more stable than a tertiary, radical, positive charge, negative charge. So that's what we would, so after the first step, we get a bromine in the benzylic position. Then we have T-butoxide. We're going to do E2, elimination. I'm actually going to do this work over here. So I hope you realize that with just that right there, the only viable double bond we can make is this one that I just dotted in black. And in fact, that's the one, because we do have a hydrogen available over there, and that's the double bond we make. Okay? And then we do a Markovnic competition of HCl. Now remember, when we protonate this, where will we put the charge? Well, we have the option of tertiary or benzylic, and we're going to go benzylic. So, when we protonate that charge right there, we will absolutely get a benzylic charge, chlorine attached from on top and on bottom. So one little tidbit about this problem is, remember, with a chlorine attached right here, you bet your bottom dollar, that is a stereocenter. And remember, when we attack sp2 carbons, there's absolutely no preference for this chlorine to attack this way or this way. So, that being the only stereocenter in the molecule, the one we just created, we will get this plus an enantiomer, okay? So that's why you would need that in this problem to get full credit. It would be that plus an enantiomer because we created a stereocenter and, in equal amounts. Racemic mixture. So, down here, what do we got? So we have AlCl3 and a acid chloride. We have a Friedel-Crafts acylation on our hands. And this group right here, I know there's a double bond, but it's an alkyl group. So we have an ortho-para director. So we will absolutely be directing this new group para, and I'll draw this over here. After the first step, still have this as well as our new 3-carbon group that has a carbonyl on it. Then we enter in Raney nickel. And I wanted to do this to show you that Raney nickel, there is H2. Some people will write it, some people don't. There is hydrogen in there. So, I believe I maybe wrote excess on the sheet. However, this will affect the double bond and that benzylic carbonyl. So your final answer, we have no trace of the double bond. We have no trace of the carbonyl. Okay, gang, I know this is getting long, but stick with me. We have a few more, so let's head on to problem 6. Okay, gang, since this is definitely going to be a longer video, for the syntheses, I'm going to throw them up here, and then I'm going to walk through them, kind of how I did them logically. So, in seeing this problem, I hope you're seeing a benzene ring and 1, 2, 3, 4 carbons in this dichloride. So if we look at our product over here, just ignore the mess that's in the middle, you can see again 6 carbons here from the ring, and 1, 2, 3, 4. 1, 2, 3, 4. Okay, so all carbons are accounted for, right? Never forget to count your carbons. So we obviously see some, we form a ring, and that always, whenever I see a problem like that, I get spooked at first. But there's not that much to this problem, I promise. So starting from the end, I hope one thing that might make sense to pick up on is we have a carbonyl here, and if you see this right here, right, 1, 2, there's an ortho relationship between there. So maybe the last step we did was a Friedel-Crafts acylation, where this alkyl group, right, was attached first. It's an ortho-para director. It slightly activates the ring. And we had, it was just intramolecular. So if we step this back with AlCl3, the structure we could have had was, obviously we would have 1, 2, 3, and 4. We have 4 carbons there, so 1, 2, 3, and 4. And on that 4th carbon, where we see that carbonyl, that's an acid chloride, right? So that, I think, stepping that back just 1 makes the problem look that much more approachable. So if you can get that, I think you can get the rest of this problem. So from there, what do we do? Well, this wasn't always an acid chloride, right? We definitely got from this source up here. So the last thing we can do, we know we get acid chlorides from carboxylic acids, and we can make that connection with SOCl2, okay? So here's the key, I think. So we've then explained how we got this, right? And we can definitely convert this Cl to a carboxylic acid. I know we can just stick an alcohol in there through SN2 and then oxidize it, right? So we have to figure out how we got this attached in the first place now. So it's on a primary carbon, so we maybe don't want to do an alkylation. So if we step this back with either the Clemmensen reduction or H2PDC or even Raney nickel, right? and hydrogen, then we could show that there was a carbonyl here, right? Stepping this back showed that we, going forward, reduce this to disappear. And this would only affect the benzylic carbonyl, not the carbonyl in the carboxylic acid. So from there, then we can also say, okay, we definitely had AlCl3. We threw in benzene, which is starting material, which is why I boxed this, meaning we already explained where that came from, as well as this acid chloride right here. So in this reaction, only this carbonyl was attached because it was an acid chloride. It won't touch the carboxylic acid. So again, from there, if we step this back one, SOCl2, because this is symmetrical, if we throw in one equivalent, we can assume that, just this carboxylic acid will become the acid chloride. And then, once we have this, you can see, okay, we just need to get two carboxylic acids where these good leaving groups are in our starting material. So if we even almost go forward, or if we go backwards, you can say, okay, we could have excess oxidized these right here, from primary alcohols, and to get these primary alcohols, we could just have excess sodium hydroxide to do SN2 to give us the alcohols to then oxidize, which links everything together. Okay, gang, that was 6. Let's do 7 and 8 and finish this walkthrough. Okay, gang, for problem 7, if we take a look at this synthesis, you can see we have propane and then this structure right here as starting material, and then we create a ring. And I hope what you're seeing is, based on this, right, we see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so all carbons are accounted for. And I hope what you're seeing here is this. Because if you see this, and especially hone in on this, we formed a ring, and there's a double bond between carbons 2 and 3. This is just the big step, if you will, this is a Diels-Alder reaction, right? So what we can do is if we step this back, right, just step it back once, start at the end, and if we have heat over the arrow, which you may or may not need, we can then draw a diene and a dienophile, right? So I think you can see with carbons 5 and 6, which is carbons 5 and 6 right here, we just have the aldehyde, right? So that's all we have to worry about, is just this group right here. And then on our diene, right, carbons 1, 2, 3, and 4, we have the O-methyl and then the isopropyl, okay? So stepping that back, that simplifies our problem dramatically, because now we have 1, 2, 3, that's gonna come from the propane, and then the 1, 2, 3, 4, 5, 6, 7, I think 1, 2, 3, 4, 5, 6, 7, all, we now know which pieces originate from what starting material. So let's start off with the dienophile. So we had to get this aldehyde, right? How do we get aldehydes? Well, we can step it back with PCC to show a primary alcohol. And I hope what you're seeing is functionality on an allylic carbon, which is no big deal. We know we can do so many things with the allylic carbon. So if we step that back, we could absolutely have done SN2 on that wonderful primary carbon. We even know allylic carbons undergo SN2 more favorably because of the conjugative effect, right? So we absolutely couldn't swap out a bromine there, and the reason why I put a bromine there is because we have a double bond. So if I was going to radical brominate, I would do so with NBS on, and this double bond could be right over here. And then where did I get this double bond? Well, I must have done E2. You could use LDA, you could use potassium tert butoxide, whatever you want to use, right? Just something that would absolutely do E2. And then, we had a leaving group, bromine, it could be chlorine as well, but you can get that from your bland old propane to start, right? So, how do we now, that totally explains the dienophile. Now, what about the diene? So, I almost kind of want to show you. So, really what you can see is that we just need to take this double bond and get 2 double bonds, right? So I'm almost going to explain this in the forward direction. So, and if you're thinking, I don't really know if I agree with this, Joe, this problem was really supposed to be more of a thought experiment to see if, to throw a Diels-Alder in there, but I also think this kind of stands as a problem. So if we put 2 leaving groups across, on both these carbons, we can do so with bromination or chlorination, right, of a double bond. that puts a bromine here and here. So now, the last thing we need to do is make a double bond here and here. In both cases, those are the lesser substituted double bonds. So when I'm going to be doing E2, I'm not going to use a small base. I'm going to use a big base, which is why I used LDA, or again, you can use T-butoxide. That will absolutely eliminate here and here, which also sets the structure up to be conjugated. So I think, you know, I have not done this reaction in real life, but I think theoretically it checks out. And then you can, so this is the S-trans format, redraw it to S-cis, finish the reaction. Okay, gang, that was 7. Finally, on to 8. Okay, gang, for this last problem, we have a synthesis right here. So from benzene and, you know, any other carbon source necessary, we have to synthesize this over here. Now, I like this problem because there's a few different relationships going on, and based on how you identify them, it will lead you down synthetic pathways that you might choose. So if we take a look over here, what I want to highlight is, as it stands right here, this group right here, that carbon directly off the benzene ring is partial positive, right? Because bromine, while I'm not saying it's fluorine in terms of electronegativity, is electronegative, certainly more than carbon. So this ethyl group with the bromine on it, that is an electron withdrawing group, right? Inductively, because this carbon is absolutely sucking electron density outside of the ring, okay? So that would be a meta-director. Now, we know what sulfonyl groups are. They're strong deactivators, meta-directors, and bromine we know is an ortho-para-director and slightly deactivates. Now, what I want to highlight is there's a para relationship here, and then there's an ortho relationship here, okay? And yes, there is also a meta relationship here. So, if we were to think about the last thing that would go on the benzene ring, I would think the sulfonyl, because that's going to really deactivate this ring, not allow for so much EAS to continue afterwards. So if we step that back, right, then we would have this bromine and then this right here, and which also checks out because this would, you know, I'm saying both of these would be terrible in terms of activating the ring, but they would direct to the same location in terms of meta and ortho, right? Because para for this bromine would be occupied, okay? So how can we take this back to this? Well, we would need this to direct, we would need some type of addition, right, to show that, you know, get these groups para to one another. So, and also try and do it in the best way possible. And the best way possible, in my opinion, would be if we put this on as an alkyl group first, then we brominated, and then we radical brominated that bromine on, which is what I show here, is that if we step this back, the last thing we would do to that alkyl group is to Br2 light and heat, which would make a benzylic radical, and then a bromine would follow. So, that's exactly what happens. Bromine radical there. So then if we step this back, so now this is a, you know, slightly activating ortho-para director. So we'll brominate, put the bromine on the para position right there. And now we need to get this going, right? And if we want to do this properly, we would Friedel-Crafts acylate it, and then your choice of H2PDC, Raney nickel, and hydrogen, or Clemmensen reduction to wipe away the benzylic carbonyl. Whew! Gang, my mouth is dry because this was a very long video with a lot of talking. If you were looking for answers for the first practice exam, I hope you've found them here. If you're watching this video, that means you financially supported jOeCHEM. So 1, thank you, and 2, I hope this website has been the tool you've been looking for to help you understand organic chemistry, excel at organic chemistry. I'm so happy you're using it right now. I hope you're using it towards the end of your organic career. But no matter what, I hope to see you all in the next video.